How you doing? I'm Mr. Rose, and today we're going to talk about capacitors in series and parallel circuits. In order to do that, the first thing we need to recognize is what is a circuit. Now, it's not the function of today's lecture, so very simply, a circuit we're defining as a closed conductive path that has a power source. That power source being my battery. A couple of things we want to point out. Symbol for a battery is one long line and one short line. The other thing, our symbol for capacitors, are since we talk about parallel plate capacitors most often, our symbol for capacitors are just two parallel lines. Be careful and distinct to know your battery has one large line and one short line. The large side stands for a positive, the short side stands for the negative. And again, two lines that are parallel, the same size, are capacitors. So, our general rule for any type of circuit: multiple capacitors in this picture, connected in any orientation. I don't care what they look like. If it's a series circuit, it's a parallel circuit, if it's a combination circuit. Any orientation are going to work as if we have one large capacitor with an equivalent capacitance. In other words, an equivalent ability to accept all of that charge. So we're starting with a picture of a parallel circuit with capacitors all connected in parallel. By parallel, we can see that these lines are parallel because that's how we draw circuits. However, that's not what we mean. A parallel circuit simply means there are multiple paths for electricity to travel. Simply put, if something happens to this path, I can still have electricity traveling in that closed path and in that closed path. Things that I need to know about these things are that each branch receives the same voltage. So I get the same potential here, there, and there while I have a parallel circuit, which means each capacitor has the same potential difference. C1, C2, C3, capacitor 1, capacitor 2, capacitor 3, all have the same potential difference V. So, capacitors connected in parallel. I'm going to replace that with one equivalent capacitor, And what that's saying is, one equivalent capacitance, which all has the same potential difference, V. So we move over here, things that I know. I know that my capacitance is Q divided by V. I can rearrange that. I know Q is my capacitance times my voltage. And I'm just doing that because it's a little bit easier to look at a linear equation. So I have Q1, which is capacitor 1, is capacitance 1 times V1, my potential difference there. I have Q2 is C2 times V2, Q3 is C3 times V3. Now what did we just say? We said that they all receive the same potential difference, which means V1, V2, V3, the potential across each one is identical. Yes, I said they are identical. If all of those are identical, that means I can simply replace it with one total V. So when I start combining my equation, I have a Q total, which is clearly Q1 plus 2Q plus Q3, is equal to my identical V times C1 plus C2 plus C3. So what I do, I divide out my voltage or my potential difference. So I have my total charge divided by my voltage or my potential difference is equal to that equivalent capacitance, C1, C2, C3, or that equivalent capacitance. In general, CEQ, my equivalent capacitor, is my total charge divided by my potential difference of any one single capacitor and or my potential difference of the battery. They all are the same thing. That is our parallel circuit. Now a series circuit is a little bit different. When I have a circuit in series, if you look at my drawing real quick, notice here I had Q1, Q2, Q3 when they were in parallel. Here I have Q, negative Q, Q, negative Q, Q, negative Q, which is probably telling you that those Qs are equal. Well, how are those Qs equal? What I mean, first of all, by a series circuit, and that's what we have here, is we're wired serially, in other words, in order. There's only one way for everything to go. Now my potential difference that comes from my battery is really only connected to two places. Here in parallel, I'm connected to multiple places. Here I'm connected to two places. Capacitor 1, the top plate, capacitor 3, the bottom plate. So I'm only connected to two places, which means all that other rearranging of charge, something else is happening. In general, we say that the capacitors in series have the identical charge on each. on each capacitor, I should say. Now, why is that? How is it possible to have this identical charge on each? Well, if I imagine a potential difference, this electricity flow, however this is happening, that knocks out an electron, well, we know we have a certain number of electrons going on in here that knocks out some charge. That charge goes from the positive plate, the top plate, to the bottom plate. Well, that bottom plate was full. It knocks out another charge down to this guy. Well, when this picks up that charge, it's going to knock out a charge. So basically, we have a rearranging of charges all due to the battery creating a potential from the top plate to the bottom plate, the only places that that's hooked up, which is telling us the two things of note, two things to keep in mind all the time with these series circuits. First of all, the charge is shifted from one capacitor to another. In series, we only have one route. I can get my electricity to go from capacitor 1 to capacitor 2, capacitor 2 to capacitor 3, that one route. Or 3 to 2, 2 to 1. One route, one path. If I have more than one path, it's not a series circuit. It's a parallel circuit. Got to do something different. The second thing is what we just talked about. The battery is only connected to the top and the bottom, which means the charges produced are only produced because we are rearranging those charges. So, what do we do next? We are going to find out the fact that capacitors hooked up in any orientation will work as one large capacitor with an equivalent capacitance. So we're going to do the same thing with a similar set of rules based on these two standards. Well, we know that my charge on each has to be the same. We know that my potential here, plus my potential there, plus my potential there, because I'm rearranging all those charges, is actually equal to the total potential difference. So my battery produces V1 plus V2 plus V3. That is the potential difference across that whole thing. So I have my general form. I know C is equal to Q divided by V. Therefore, I know V is equal to Q divided by C. So I have V1 is equal to Q divided by C1. V2 is equal to Q divided by C2. V3 is equal to Q divided by C3. Again, because all of those charges have to be equal. Well, I start rearranging equations again. I know my V total is simply V1 plus V2 plus V3. I can factor out my Q equal to 1 over C1 plus 1 over C2 plus 1 over C3. Right there, that's my equivalent capacitance. I know it's kind of squeezed in there. I was running out of room. So I divide both sides by Q. I have V total divided by Q is equal to 1 over C1 plus 1 over C2 plus 1 over C3, where that is my equivalent capacitance. I take the reciprocal of that, simply said, for a set of capacitors hooked up in series, my equivalent capacitance C is equal to my charge on any one single capacitor, because they all have to be equal, divided by the total potential difference. Another way to say that is 1 over CEQ. That's how I find my equivalent capacitance. 1 over C1 plus 1 over C2 plus 1 over C3, etc. That's what I can put in right there. Or my general form, 1 over my equivalent capacitance is equal to the sum from 1 to n, however many capacitors I have, of 1 over C sub I. That's all I have for you today. Please feel free to like, comment, or subscribe. And remember, you can do all of this. You have the capacitance. See you next time.